So first, I would like to thank I think we have still 2 organizers here, so thank you very much for for the food and for yeah, for organizing this meeting. It's been really interesting, like getting to know all of you. And I'm going to present the work we've done in the university, in the Complutense University of Madrid, and we've been working on the. Our group works in complex oxides, and we are starting to do kind of a Moiré and topological induced structure. So we are kind of new to the field. But first of all, I need to show you like an alert, because this is not a talk about CR, SBR. So for those of you that want to leave, just please go outside. I mean, it's okay. We have the lunch just there. Anyway, so this is going to be about ferroelectrics. So this is my group in Madrid. So we are quite a big group. We are like 25 people, and we are working in different topics, but we do everything from crystal synthesis, growth. We do lithography. We do devices. We are doing neuromorphic computing, and we are also doing now 2D materials and twisting. And in my lab, we are responsible like for the electron microscopy characterization, and we are in the Complutense University in Madrid. And I'm going to present the work we've done in collaboration with people. So this is people in my group, people in the Institute of Material Science of Madrid, in the group of Andres Castellanos, who is the guy that had all the experience for the 2D materials, and also the theory was done in the Luxembourg Institute of Science and Technology in the group of Jorge Iñiguez. So, and of course, just to acknowledge all the funding agencies. And so this is the outline of the talk. This is a bit of a spoiler, but this is what we are going to get to in a few slides. And I'm going to show you what are these topological polar structures, why are they different from the magnetic topological structures. I'm going to show how we can create this structure using freestanding oxide layers, and I'm going to just give you like a very tiny lecture on aberration electron microscopy, just to make sure we are on the same point, and I will show how we can stabilize these 2-dimensional vortex patterns in these twisted ferroelectric layers. So first, for those of you who are not familiar with the ferroelectrics, this is the unit cell of barium titanate, which is the material that I'm going to be talking about. This is a perovskite material. So we have our A atoms, these barium atoms in the corners of the cube. We have the titanium in the middle and the oxygen in the center of the faces of the cube. When we have this is a cubic structure. If we have a ferroelectric state, then the atoms, like the positive, like the titanium and the oxygens, will be displaced from each other. We will have like an electric dipole for each unit cells, and then we have a ferroelectric polarization. So the one thing that is usually when we have this kind of the structural distortion, this is going to be followed by a change in the lattice parameter of the material. So this is going to be elongated along the ferroelectric direction, like along the polarization direction, and it's going to be constrained in the other direction. And this is the reason why the structures that I'm going to show you were not supposed to be stable. So I'm going to show you again the same the diagram that Fernando showed yesterday from his advisor, where they calculated all the ferroelectric topological structures that were supposed to be stable. So we can have vortices and anti-vortices, skyrmions, vortex lines, and but these are very different from the magnetic structures. So because in the magnetic structure, so the order parameter is the spin, and it can rotate freely, but in the ferroelectric materials, the order parameter is the polarization, and it goes with the distortion of the lattice. So this is a very energy costly effect. So this continuous rotation of the polarization is supposed to be very high. So it costs like a very high energy. So having this continuous rotation of the polarization comes with a very with a very high energy cost. So in order to stabilize these kind of structures, people started doing these super lattices, like Fernando showed yesterday. So they started mixing these paraelectrics with the ferroelectrics, with different thickness layers, with different materials grown on different substrates. So you will have tensile strain from the substrate, compressive strain from the substrate, and people were able to stabilize this kind of ferroelectric vortices, also this kind of these ferroelectric bubbles, and also more recently people have been trying to do this polar voltage and with like a modulation, like a chiral modulation in 2 dimensions, in the in plane and the out of plane dimension. So to stabilize all these kind of phases, they had to very carefully choose the material. So you have a polar discontinuity at the interface. There is a different strain, so there are strain gradients that are coupled with the ferroelectric polarization at the interfaces, and also you have so you have to carefully choose the mechanical boundary conditions of these little structures to be able to stabilize. So there is like a trade-off between the elastic energy of the strain, the electrostatic energy of the polar discontinuity at the interface, and the strain and the polarization gradients. So if you are lucky, or if you calculate all these parameters, you can stabilize this kind of polar like topological structures with the ferroelectric materials. But all these systems they are still they are constrained due to this epitaxial growth of the ferroelectric layers. So usually when we do complex oxides and when we do ferroelectric, we will have a single crystalline substrate, and we will grow our atoms on top with a pulsar laser deposition or sputtering or whatever, and we have this atom by atom replication of the structure. So if you have here, like the mechanical boundary conditions that we can apply at the interface are limited basically by the lattice parameter of the substrate, so we can do either compressive strain or tensile strain. So the strain landscape that we can create are very limited. So our idea was to get rid of these constraints by freeing the layer. So this is what we did. So basically we grow the epitaxial layers and then we delaminate the layer, and now we can play with it and we can create different strain landscapes. And to do this, we are going to use our single crystalline substrate, which is this extrusion titanate, which is one of the most common substrates used for the complex oxide growth. We are going to grow 2 layers. One is going to be this lanthanum extrusion manganate layer, and the other one is going to be our ferroelectric barium titanate layer. And we are going to put one of these PDMS or one polymer on top of the structure, and we are going to submerge this structure in a glass with an acid that is going to selectively etch the manganese layer. So this acid is going to only etch the manganese atoms. It's going to remove this layer, and after a few hours or maybe even like a few days, we are going to end up having our ferroelectric epitaxial layer stick to the polymer, and our substrate will just drop to the bottom of the glass. So we can have this kind of a 2-dimensional ferroelectric layer on our polymer. And for those of you who work with the 2D materials, now we can just do whatever we want with it, right? So I'm going to just quickly show a video done by one of our students on this exfoliation process. So you can start to see how the gray color starts coming from the edges of the crystal, and we are removing this manganate layer. And after a few hours, then this will be completely removed, and we have our freestanding ferroelectric layer. So we will have something like this. This is an optical image. You can see a bit there, the layer, and then we can use like conventional deterministic transport just to do whatever we want with it. So these layers, we check the properties of the layers, just of a single ferroelectric layer. It's still ferroelectric, which is the most important thing. it has the structure and the composition is still intact, and we see this is interesting. So when we are delaminating the layer from the substrate, it's not constrained by the epitaxial match with the substrate, and it recovers like the lattice parameter of the bulk. So we are getting like bulk life few nanometer thick ferroelectric layers. And now we can just stack it with any other material, with other three-dimensional materials, other 2D materials. We can do twisting, we can do whatever. And for example, one of the first things we did with it was making these high-performance transistors, mixing it with conventional 2D semiconductors. So we can just transfer our barium titanate layer, which is a very high dielectric constant material, and we put our one monolayer molybdenum disulfide on top, and we have a transistor. And because of the strong polarization and of the barium titanate layer, we can have this kind of characteristics in the transport measurement where we have a very big hysteresis due to the polarization switching up and down in the transistor. So we can now use this kind of materials to design like new devices. But the thing that we were most interested in was starting to do this twisting. So I'm going to show this the same animation that I was showing before, basically. So we can do some twisting of the layers. So we are going to transfer 2 layers. This is the single barium titanate layer, which is 15 nanometers thick. So this was a bit thicker one. We are still trying to optimize all the delamination and the transfer process, because we have some cracks, we have some holes still, but this is a 200 micron scale bar, so that we can still get like big flakes, like single crystalline flakes, and we are going to transfer a second layer twisted by 10 degrees in this case. And to study this structure, which basically we have these 2 twisted barium titanate layers, is where we are going to use the aberration corrected electron scanning transmission electron microscope. And here comes the 2-minute lecture. So for those of you that are, well, I suppose that most of you have already seen these kind of images from the STEM microscope, like atomic resolution images from the STEM microscope, and we can do atomic resolution chemical mapping. We can study also like the electronic properties of materials, looking at the fine structure of the edges of the different materials. And this is now, so this was not that common like 15, 20 years ago, but now it's kind of routine. So we can do these kind of measurements very easily. And this is all thanks to this part of the microscope here, which is the aberration corrector. So in the microscope, we are using magnetic lenses, and usually we have spherical symmetry magnetic lenses, but these have some aberrations, right? So we use this aberration corrector, which is a set of magnetic lenses with different symmetries. We have quadrupole, hexapoles, octupoles, etc., to shape kind of fix the shape of the probe and correct the aberrations. And this is very important for this work, because one of the things that we can do with this is opening the aperture that we use to form the probe of our microscope. So this is the aberration function. So this angle here is the angle from the optical axis to the edge of our aperture that we are going to use to form the probe. And if we open the aperture more, we are going to have a more convergent beam. And having a more convergent beam, we are going to improve the resolution in the 3-dimensional direction. So we are going to have something like this. So this is a more conventional microscope now with an aberration corrector that has a 30 milliradian convergence angle. So the probe is convergent, but not too much. But if we increase with the new correctors, if we increase this angle, we are going to improve our resolution in the depth section, in the 3-dimensional direction, basically. So we are now using like 5 nanometer resolution, and we want to increase, and we will get down to 1 unit cell resolution in the Z direction in a few years. And for example, we can identify the position of dopant atoms within a crystal, inside the crystal. And using this kind of technique, which is called this large angle illumination depth sectioning in the scattering transmission electron microscope, we can study these twisted ferroelectric structures. So this is a video of one of the samples. We are looking from the top, and we are going to change the defocus of the probe, doing this depth sectioning experiments from the top layer to the interface of the two layers, and then to the bottom layer. And you are going to see how we can see the top layer, and then we are going to start seeing the bottom layer, and then when both layers are focused at the same time, we have the Moiré contrast, and then we go to the bottom layer, and we can study both layers independently, which is very, very important for this. I'm going to play this again, maybe, yes. So we are focusing the top. We go through the middle of the samples to the interface. We see the Moiré contrast, and then we exit the sample in the bottom, right? So we have a look at the Moiré contrast in the middle. We have this kind of very similar structure that we had with we twist any other material or any 2D material, and we have these are two layers that are twisted by 10 degrees. So we have this kind of Moiré features here, and this is like the model of the two twisted layers. And I'm going to refer to these two structures within the Moiré, which are these AA and these AB stacking regions where we have highly coincidental sites between the titanium atoms on the top, titanium atoms on the bottom, or in the AB, titanium atoms on the top, barium atoms in the bottom, right? So we have these two kind of structures that form a Moiré lattice in our twisted bilayers. So and we are going to be doing this depth section experiment. So we are going to focus on the top layer. We are going to analyze the structure of the top layer, and we are going to relate the things we see in the top layer with the position of this A and this AA and this AB regions in the Moiré. So first, this is a ferroelectric material, and we have this displacement of the titanium atom from the center of the unit cell, and we have this non-centrosymmetric structure. We can measure these electric dipoles for each unit cell, and we can and if we do that, we get this map of small arrows, which are just showing you the shift of the titanium atom from the center of the unit cell, and you start to see how there are some kind of curling occurring here of this ferroelectric polarization, right? And if we calculate, just to make it a bit more clear, if we calculate the toroidal moment of this vectorial field, which is basically just the product of the position of the dipole by its ferroelectric polarization, we can visualize this toroidal moment, which is something like this. And now we can still start understanding a bit what we have here. So we have this positive, which are the blue ones, and the negative, which are the red ones, vortices with clockwise and anti-clockwise direction, both which are with a +1 winding number, and in the middle we have these anti-vortices. So due to this twisting of the layers, right, we are going to have in the top layer, we are going to have these ferroelectric structures, which are in this case, they are very, very, very small structures, just like at 6 unit cells in size, of polarization vortices that are going to be rotating clockwise, anti-clockwise, clockwise, anti-clockwise, forming this lattice of vortices and anti-vortices. And if we study not only like the displacement of the titanium from the center of the unit cell, but we study the lattice perimeter and the distortion of the unit cell itself that I showed you in the beginning, when we have this polarization, the unit cell is also going to be distorted, right? We get this kind of strain landscape. So this is measuring basically, this is coming from the structure of the unit cell, so from the barium lattice only. And we have this shear strain, so this is this kind of twisting strain, and we are going to have a lattice of positive and negative cores of the shear strain that are going to be just in the middle of the highly coincidental sites. So the vortices are aligned with this AA and this AB region, where we have the coincidence of the barium over barium or barium over titanium, and in the middle, where we have the biggest deformation of the lattice, of the biggest mismatch between the two lattices, we have this positive and this negative shear strain cores. And the interesting thing with this is that we can, so this is kind of how it looks like all together. And as we are just transferring these two materials and we are just doing twisting between two different layers, we can select the angle, so we can create these topological ferroelectric structures with the size we want. So, for example, here we have this. In these ones, we have vortices of around 2 nanometers or 2.3. If we do like a lower twisting angle, we are going to have larger vortices of around 10 nanometers. So, in comparison with like with the experiments that the community was doing before, where they have to carefully choose the thickness of the layers and the materials in the layers, so the sizes of these ferroelectric structures were fixed by the thickness of the layers. In this way, we can create different strain landscape with different periodicity, and then create these polar vortices with different sizes. And to explain all of this and all these phenomena, we ask our theoretician friends from Hugo and Jorge from the Luxembourg Institute of Science and Technology, and they did an DFT calculations where they imposed the ferroelectric polarization, and they let the lattice relax, and we got the same kind of shapes, the same kind of modulations. And the explanation for this modulation comes from this effect here, which is the flexoelectric coupling. So when you have a ferroelectric material, this is always coupled with the structure, so the ferroelectric polarization and the structure are always strongly coupled. So if you calculate the gradient of the strain along the vertical or the horizontal direction, this is going to be coupled with the ferroelectric polarization. So you get the gradient of the strain, it gives you these kind of stripes, and if you look at the arrows, which are the ferroelectric polarization, for a positive for a positive gradient of the shear strain, we are going to have arrows pointing up, and for a negative gradient, we are going to have arrows pointing down. So the gradient of the strain is going to pin our ferroelectric polarization, and the same is going to happen for the other direction, right? So for the positive shear strain gradient, the arrows point right, the negative one, the arrows point left, and this is pinning the polarization. And this is like the final view. So we have this kind of a diagram here where we have this lattice of positive shear strain and negative shear strain cores that are going to pin our polarization and are going to create these ferroelectric vortices. And just to summarize and end my talk, I hope I show you how we can stabilize these kind of states by twisting these ferroelectric layers. And the important thing about this is that these are the smallest ferroelectric objects that have been stabilized up to date. We can do ferroelectric objects of just a few nanometers. So the idea for those of you more focused on the application and engineering part is that we could use this as a kind of a memory device with very high density storage. And I would like to thank you for your attention. Thank you.